Welcome back to the second video in Tech 240 for Wednesday, April 7th. In the previous video, we talked about capacitors and capacitance and how to add them in a circuit in series and in parallel. We also talked about reactance and how to add reactance in series and in parallel. And in the last bit of the last video, we talked about how to solve some simple AC circuits. Those were only AC circuits that were purely capacitive. So those circuits only had an AC voltage source and a capacitor. If they only have a capacitor and they don't have any resistance in them or inductors, then we call that a purely capacitive circuit. And if we have a purely capacitive circuit, then we can solve that using a modified form of Ohm's law, where we just replace the R, resistance, in Ohm's law with X, reactance. So we can actually use the equation V equals IX for purely capacitive circuits. So that's pretty convenient. It's nice to recognize that, because if you ever encounter a situation where you can idealize or assume that a circuit is purely capacitive, then by all means use V equals IX. You still have to calculate the capacitive reactance, X, to get X. But then once you have X, it's really easy to plug that into V equals IX to find whatever else you need to solve for. So that only applies, I need to stress this, that only applies for a purely capacitive circuit. And because of that, it's not really that useful in the real world, because there aren't that many circuits in the real world that are purely capacitive or even close to purely capacitive. In the real world, every real circuit actually does have some resistance in it. Even if it doesn't have a resistor, it still has wires that connect the different components, and wires have some small value of resistance. So in the real world, you will never really encounter a circuit that doesn't have any resistance in it. So if we have a circuit that has capacitors, it probably also has a resistance in it as well. So we have to come up with a new term. And you may have heard this term before. You may not have used it, but you may have heard of this term. The term is impedance, impedance. And the abbreviation for that is Z, capital Z. And impedance is going to be the term that we use to combine the effects of resistance, which does dissipate energy in the form of heat, combine resistance with reactance. Reactance, as we said in the last video, does not dissipate any energy. It just charges the capacitor and then discharges, and then charges and then discharges. But you still have to account for that energy that is being used to charge and discharge, charge, discharge. All right, so impedance combines those effects of resistance, which is dissipative, it dissipates energy, and reactance, which is not dissipative. All right, so we're going to talk about how we're going to combine those terms into the term of impedance, and we'll talk about how we use impedance to solve more realistic AC circuit situations. So with that, I'm going to share my slides. All right, so because purely capacitive and purely inductive circuits don't exist in the real world, we need another term to combine the effects of reactance and resistance, and that term is impedance. All right, so what you should think of when you think about impedance, it's actually the combination, but it's not just the algebraic sum of reactance and resistance. It's actually the vector sum. And we're not going to talk too much about vectors, but what you should think about is that this forms a triangle. The horizontal part of the triangle is the resistance, R, the resistance. The vertical component of the triangle is the reactance, X, and then the hypotenuse of the triangle is the impedance, Z. All right, so once again, the horizontal part of the triangle is the resistance, R. The vertical part of the triangle is the reactance, X, and the hypotenuse part of the triangle is the impedance, Z. And you might remember the Pythagorean theorem from geometry, a squared plus b squared equals c squared. where A and B are the two sides, the horizontal side and the vertical side, and the C is the hypotenuse. So this side squared plus this side squared equals the hypotenuse squared. So if you know what the resistance is and you know what the reactance is, then you can find what the hypotenuse is through the Pythagorean theorem. All right, so impedance is a combination, it's a vector sum using triangles of the resistance and the reactance. The units for impedance, Z, are ohms, which is, I think, quite unfortunate because I think it leads to confusion because impedance and reactance and resistance all have the same units of ohms, but they're not the same thing. Impedance is not the same thing as reactance, and reactance is not the same thing as resistance. What's pretty interesting and really convenient is that to do AC circuit analysis, we can use Ohm's law if we modify Ohm's law, and instead of using R for Ohm's law, or for using X when we had a purely capacitive circuit, we can use V equals IZ for an AC circuit after we calculate the impedance. So if you're doing a circuit like this, if you're doing an AC circuit analysis circuit, and it has resistance and capacitance in it, then you're going to want to identify what the resistance is. You're going to identify what the capacitance is, and then convert that capacitance to reactance. Now you have the reactance and the resistance. Once you have those, you can calculate the impedance by taking the resistance squared plus the reactance squared, and then finding the hypotenuse, because a squared plus b squared equals c squared. So take a squared, add it to b squared, then take the square root of that sum to find c. All right, so we can use V equals IZ for AC circuit analysis, and that's what you're going to do in the next lab. Think about what happens in this triangle if we have a purely capacitive circuit. If we have a purely capacitive circuit, then there is no resistance. There's only capacitance and thus reactance, right? And if there's only reactance, no resistance, then this part of the triangle is zero. And therefore the hypotenuse is the same thing as the reactance, all right? So this makes sense. V equals IX is what we have for purely capacitive circuits because there's no resistance. But if we have a resistance, then we have to include that in the triangle, all right? All right, so we've said this, Z is a vector sum of resistance and reactance. And let's do a circuit like this. We've got a series RC circuit. That means we have in series a resistor and a capacitor. And here's our values. And we know that the impedance is given by this equation because I have a squared plus b squared, a squared plus b squared equals c squared. But I don't want c squared, that's the hypotenuse squared. I want c, that's the hypotenuse. So to find c, I take the square root of a squared plus b squared, right, in the Pythagorean theorem. And so that's going to get me the impedance, z, equals the square root of the sum of a squared, which is the resistance, plus b squared, which is the reactance. All right, so this is your equation for a series RC circuit to find the impedance. And we can use Ohm's law, V equals IZ. All right, so if we have a purely resistive load, so there's nothing, there's no capacitor in here, there's no inductor in here, there's nothing that can cause a phase shift of the current relative to the voltage. Remember how we said that in a capacitor, current leads voltage? Well, in a resistor, there's no phase shift at all. So the current in, let's say, the yellow curve is exactly in phase with the voltage, let's say, in the white curve. So there's no phase shift. But, and this is foreshadowing to next time, if I have an inductor here, this is an inductor, and we'll talk about that next time. If I have an inductor, now I have a phase shift, because what we're going to say next time is that in an inductor, the current lags the voltage. The current comes after the voltage. So this is what the waveform looks like when I have an inductor in the circuit. Here's the voltage, but the current, you can see, is lagging. The current comes behind the voltage. Voltage goes up here, current goes up here. Voltage goes down here, current goes down there. Whatever voltage does, current does it a little bit later. So if I have a slightly inductive load, that means my inductance, or inductor, is small relative to the resistor. And if I have a slightly inductive load, then I have a small lagging phase shift. If I have a large inductive load, then I have a larger phase shift. The current lags the voltage waveform by more. And if I have a purely inductive load, then it's going to lag, current is going to lag voltage by a full 90 degrees. We haven't talked about inductance or inductors yet, but we will next time. And this is just foreshadowing. So you're ahead of the game for next time. We talked about capacitors today. So if we have a slightly capacitive load, that means the capacitor is small relative to the resistance. So think about that triangle where the resistance is large and the reactance is small. If the capacitance is small, then the reactance is going to be small. So I have a large resistance and I have a small reactance. That's going to result in a small phase shift. Since it's capacitive, it's going to be leading. Current's going to be leading the voltage. So you can see here, current does whatever voltage does, but a little bit before the voltage waveform. So here in this waveform, current is leading voltage by a little bit. If the capacitor is larger or the resistor is smaller, in other words, I have a larger capacitance relative to the resistance, then I'm going to have more of a leading waveform. So now my current is leading the voltage waveform by a little bit more than it was before. And if I have a purely, if I have a purely capacitive waveform or circuit, purely capacitive circuit, then my waveform is going to look like this, where the current is leading voltage by a full 90 degrees. And when that happens, whenever one curve has a peak, the other is crossing the zero axis. This is pretty close. Yeah, this waveform is pretty close. Yeah, it should show that whenever one curve has a peak, the other one is crossing the zero axis. And since it's leading, in this case, since current is leading the voltage, the current is doing whatever the voltage waveform does, but just a little bit early, before the voltage waveform. We'll talk about this later on, but again, just a little bit of foreshadowing here. If capacitive circuits cause current to lead voltage, and if inductive circuits, that we'll talk about next time, if inductive circuits cause current to lag voltage, then what if you have an inductor and a capacitor? What if you have both in the same circuit? Could they cancel out? The answer is yes, they actually can cancel out. And if you can match them up perfectly, such that the capacitive reactance matches up with the inductive reactance, then you can actually get back to the point where your current is in sync with your voltage waveform. We'll talk more about this in a couple of weeks, but this is actually the way that it's most efficient to operate the electric grid. We would not like to operate the electric grid like this. This is actually an inefficient way to operate the electric grid. We would like our current waveform to be as close to in phase with the voltage waveform as possible. We'll talk about why in a couple of different, couple of class sessions. But for now, I'm going to leave it like that with the idea that you can have these effects cancel out. Inductive reactance can cancel out capacitive reactance. I think it might be useful to end with an example here. So here is a simple AC circuit. We've got a voltage source that is 240 volts at 100 hertz. That's kind of a weird frequency, but whatever, we can deal with it. And we've got a resistance that is 200 ohms, and we've got a capacitor that is 5 microfarads. And we want to find the current that is flowing through this circuit. All right, obviously it's going to be AC current, but let's find what that AC current is. We know that we can use this modified version of Ohm's law, V equals IZ, and we could rearrange to find I equals V divided by Z, but we don't know what Z is, so that doesn't really help us yet. But we know that there's this relationship like this triangle between R and X and Z, which is to say that Z, the impedance, is the vector sum of resistance and reactance right here. So we want to try to find resistance, we know that, and we want to try to find reactance. We don't know that yet, but we need to find that. And fortunately, there's a pretty simple equation to find the reactance. All we're talking about here is the capacitive reactance, because there's just a capacitor here. Capacitor is the only component here that has a reactance. Resistors do not have reactance to them. So this has a resistance R, and this has an associated reactance X. All right, so our equation for capacitive reactance is 1 over 2 pi Fc. Make sure that you put the frequency in hertz, and make sure that you put the capacitance in farads. This is probably the most common way to mess up this type of problem, is to mess up what you put in here for the capacitance. What you need to put in there is 5 times 10 to the minus 6. Don't forget that part right here. If you just put in 5 right here, because you see that it says 5 microfarads, and so you put 5 in right here, and you forget about this part, then you're going to come up with a very, very wrong answer, off by a factor of 1,000,000. So make sure you convert that to farads when you put it into this equation. All right, so we got 1 over 2 pi times 100 hertz times 5 times 10 to the minus 6 farads. Put that into your calculator, and you should get a X sub C, capacitive reactance, equals 318.3 ohms. Remember, the units for resistance and reactance and impedance are all ohms, unfortunately. So now we have X, our capacitive reactance, and we have R. So we can use the Pythagorean theorem, a squared plus b squared equals c squared, to find the impedance, which is the hypotenuse here. All right, so this is our A, this is our B, this is our C. So a squared plus b squared equals c squared. In other words, r squared plus x squared equals z squared. But we want z, not z squared. So take the square root of both sides, and you get z equals the square root of r squared plus x squared. Now we can plug in for R and plug in for X. Make sure you square them. So 200 ohms squared plus 318.3 ohms squared. And you'll find that the impedance is 375.9 ohms. That's our hypotenuse right here. And now we're in business, because now we can use this equation. Now we finally know Z. And we know V because V was given, so we can find our current I. So just rearrange this equation for current to find that current equals V divided by Z. Plug in numbers there, and you get 240 volts divided by 375.9 ohms, and you get a current of 0.64 amps. All right. Note that this current, because you have a capacitor in the circuit, you're going to have a leading, I should maybe say current, maybe specify this more clearly. Current is leading the voltage waveform. All right, so this current is leading the voltage waveform. All right, that is a good place to stop for right now. So in this video, we talked about impedance, because we said that in the real world, purely capacitive circuits for which we could use the equation V equals IX, they don't really exist, except kind of in the hypothetical. So in the real world, we always have some resistance in the circuit. And if we have some resistance in the circuit, then we can't use just reactance, and we can't use V equals IX. We have to use impedance, Z. And to calculate Z, we use the Pythagorean theorem, because it's just a vector sum. Picture this triangle, where this side of the triangle is resistance R, this side of the triangle is reactance X. The hypotenuse is what you want to find. That is Z, impedance. So to do that, you take a squared plus b squared equals c squared, but you want to find C. So to find C, you solve for C by saying C equals the square root of a squared plus b squared. All right, and then once you have Z, the impedance, then you can use V equals I Z, where you're basically using Ohm's law, but replacing R with Z, the impedance. All right, you are now ready to do the next lab on capacitors, lab 15. I'm also going to help you out a little bit. If you look at the capacitor lab on the back page of the lab, you do not have to do number 9, number 10, or number 11. All right, so on the capacitor lab, lab 15, you need to do numbers 1 through 8, as well as 12 and 13. All right, so we didn't quite get to the point, and I don't really need to. I don't really want to go quite to the point where we cover the material for numbers 9, 10, and 11. I'm sure that you could figure it out using the capacitor formula sheet on the previous page from lab 15. There's no doubt in my mind you could figure that out, but I'm not going to make you. So lab 15, all I'm looking for is for you to complete numbers 1 through 8, as well as 12 and 13. All right. For number 12, it's a little bit tricky to draw those waveforms, but you can do it. Remember, my hint is to, whenever you see a peak in the waveform, so in number 12, there's the voltage waveform. When you see a peak, draw a dashed line from the peak, the positive peak or the negative peak, down to or up to the 0 axis. And your current should cross the 0 axis whenever the voltage is at a peak. All right. Okay, and every time the voltage waveform crosses the 0 axis, your current waveform should be at a peak, either a positive peak or a negative peak, a maximum or a minimum. All right, so that's my hint. Take your time with it. You can look back through the slides. That will help you as well. And you can do number 12 and number 13. Maybe it might help you out a little bit if we clarify that number 12 is for a purely capacitive circuit. All right, so it says draw a line, a curve that represents capacitor current on the graph with capacitor voltage. So let's say this is a purely capacitive circuit. You're given the applied voltage. What does the current in that circuit look like? Draw that waveform, okay? All right. Number 13 is just in general. What can you say about current in a capacitor compared to the voltage applied to the capacitor? All right, that's going to wrap up this class session. If you have any questions, as always, let me know. Come to my office hours, shoot me an email, get in touch with me somehow. I'm happy to help out. Otherwise, have a great weekend, and I'll see you next time.